Industrial automation used to be defined by isolated programmable logic controllers driving single pieces of machinery. Today, those standalone devices have been integrated into expansive networks of hardware and software. This is the modern cyber-physical production system. It is the strict, deliberate integration of physical actuation on the factory floor with high-level data processing in enterprise IT networks. These systems perform production tasks with minimal human intervention to drive specific, repeatable improvements in throughput and product quality. This dashboard shows the exact metrics used to judge these systems. Success is quantified through overall equipment effectiveness, reduced cycle times, precise tracking of mean time between failures, and meeting rigorous safety integrity level targets. To understand how engineers achieve these targets, we have to build the architecture from the ground up, starting at the physical bedrock of the factory floor and moving all the way up to the enterprise IT layer. True automation requires engineering a seamless flow of data across multiple levels of hardware to generate systemic, plant-wide efficiency. We start at the bottom, the power and actuation layer. This is where digital control commands are converted into raw physical work, relying on electromechanical subsystems and power electronics. This schematic details a multi-level inverter topology, which is required for driving medium and high-power motors. Notice how the unstable, jagged red harmonic distortion waves on the left are smoothed into clean sine waves. By mitigating electromagnetic instability and reducing leakage currents, engineers can safely apply aggressive adaptive frequency control without prematurely degrading the physical equipment. The empirical impact of this hardware optimization is significant, particularly in heavy continuous process operations like marine engineering. This chart compares energy consumption for seawater cooling pumps. Against a baseline of constant speed operation, intelligent adaptive frequency control yielded a 90.5% reduction in laboratory testing and sustained savings above 80% during full-scale sea voyages. The system maintained strict thermal safety margins and preserved the health of the physical pumps throughout the trials. Implementing this requires precise sizing calculations. Before writing a single line of code, engineers must calculate transient torque, thermal limits, and fault current capacity based on the demands of the control architecture above. The efficiency dictated by high-level software algorithms can only be realized if the physical hardware topology at the actuation layer is capable of executing it. Moving up one tier, we reach the program of instructions. This is the domain of programmable logic controllers, executing rigid ladder logic to govern the physical machines below. This fast loop illustrates determinism. A deterministic system guarantees millisecond-level response times. This absolute predictability is non-negotiable for safety guarding and basic process regulation. To ensure that speed, algorithmic controllers like proportional integral derivative loops or model predictive control are embedded directly onto the PLC hardware, locking in closed-loop behavior at the local level. In a pharmaceutical batch mixer, for example, a single PLC strictly orchestrates the temperature parameters, the exact ingredient sequencing, and the agitation speed. Because the PLC executes its logic in a perfectly rigid, unbroken cycle, the resulting continuous process is highly repeatable and legally validated. Complex scheduling and heavy mathematical optimizations are deliberately excluded from this layer. Processing those tasks would interrupt the critical fast loop and delay actuation. When logic updates are required, engineers rely on modular program structures and tight version control, minimizing the risk of introducing errors into the physical operation. Strict separation of this deterministic execution layer guarantees that physical safety interlocks are never compromised by data processing delays originating higher in the network. Sensing and feedback components close the gap between the physical actuators and the logic layer. Modern smart sensors and inline vision systems perform local processing to filter and analyze data directly at the edge. Filtering noise at the point of collection significantly reduces the sheer volume of telemetry that must be transmitted upward, preserving critical network bandwidth. That refined data feeds directly into the supervisory orchestration layer, which consists of SCADA systems and building automation and control systems known as BACS. While a local PLC controls a single machine, A BACS coordinates the complex sequences and overlapping dependencies of disparate machines across entire plant areas. The Doha Metro provides a prime example. Its building automation system integrated redundant hardware with SIL-capable fire life safety functions, accelerating the commissioning time for the entire public transit network. At this tier, SCADA systems manage operator situational awareness. They translate raw data into human-machine interfaces, managing complex alarm hierarchies so operators can monitor the plant safely. The historical telemetry archived by these supervisory layers serves as the definitive record, used to shorten troubleshooting cycles and conduct rigorous safety audits. The supervisory layer transforms isolated machine logic into a coordinated, auditable operation across the entire plant, while maintaining the safety integrity of the underlying hardware. The primary technical challenge is bridging operational technology on the factory floor with non-deterministic enterprise IT and cloud layers. The traditional hierarchical automation model relied on strict, isolated vertical tiers. However, those rigid boundaries bottlenecked advanced data analytics, keeping intelligence away from the physical machines. This diagram illustrates the transition to a hybrid IT-OT integration model. Rigid horizontal boundaries dissolve into a fluid, node-based cross-layer network. This architecture relies on interoperable communication stacks like OPC-UA and MQTT to translate industrial sensor data into formats that enterprise algorithms can process. To utilize this data effectively, engineers employ a co-design approach. They deliberately pair the short, deterministic response loops of the PLC with powerful edge AI analytics nodes. Closed-loop digital twins and edge inference models operate in parallel to the physical machines, running continuous simulations of the local environment. By analyzing historical telemetry, these predictive models compute optimized parameters and feed highly accurate setpoint recommendations back down to the machine controller in real time. Because the AI processing is co-located at the network edge, physically close to the machine, it completely bypasses cloud latency to support ultra-low latency optimization. Breaking down the traditional hierarchical model allows engineers to inject high-level predictive intelligence into physical manufacturing without breaking deterministic safety. This is the complete cyber-physical stack in operation, moving from the physical actuator, through the PLC, into the SCADA system, out to the edge gateway, and up to the cloud. Observe the system's reaction during a simulated disturbance, such as a severe thermal spike inside a high-power motor. The smart sensor detects the anomaly. Instantly, the PLC executes its deterministic fast loop, automatically limiting the inverter to maintain physical safety. Simultaneously, the slow loop activates. The SCADA system logs the thermal event, and the edge AI ingests the data to update the enterprise maintenance schedule. The strength of modern automation lies in these strict functional boundaries. Deterministic safety remains firmly locked at the embedded controller, while intelligence is abstracted to the edge. Ultimately, by engineering this multi-layered framework, a localized physical control loop natively scales into measurable, enterprise-wide operational intelligence.